Good morning, good afternoon, good evening, everyone. Welcome to the TFTC webinar series. I am Garyong from Georgia Tech as usual. We are back just in a week with a little bit different time. Thank you for being with us today, despite the time change of 2 hours. You will never regret to be here today as we have a wonderful speaker, Dr. David Khan. Today, David will share his new perspective about reimagining traffic in the era of increasingly automated electric vehicles. Dr. Khan is an assistant professor at Florida Atlantic University. Prior to joining FAU in 2019, he had been a lecturer and postdoc at UC Berkeley, where he received his PhD in transportation engineering. He has rich experience in empirical research related to advanced driver assistance system and vehicle automation, and he offers a unique perspective on the potential opportunities of electric vehicles. Now, all that said, please join me in welcoming David to the webinar. Now the floor is yours, David.
Well, thank you for the introduction, and I want to thank everyone for taking the time in the morning, especially if you're in a different time zone, west of the Eastern time zone, for example. I know it's quite up and early for you guys. Hopefully, I'll be able to wake you up and electrify you with our discussion on electrification. So if you're in this webinar series, you probably care somewhat about traffic congestion. Well, if you're like me, who has quite a bit of a long commute, you're going to care a lot more about traffic congestion. So I commute daily on the infamous Interstate 95 and a little bit of Interstate 595 for about a total of 30 miles. And traffic congestion is really not just a modern day problem that has been around really since the beginning of just automobile mass production. So this is a picture of the San Francisco-Oakland Bay Bridge back in the 1930s. Yes, there was traffic back in those days. And that's what started this whole discussion about traffic flow and how do we quantify traffic congestion, at the same time, how do we manage traffic congestion? And this started with a few experiments using consecutive pictures of moving cars. Back in those days, that's the camera technology we're talking about. So in addition to the empirical data collection, where we're able to explain traffic by building models. Here's kind of an original sketch of the fundamental diagram. This is, at this point, if you're in this webinar, this concept is very familiar to you. By having a better understanding of traffic, we also got to a point that that we had different control strategies. A lot of innovations in traffic control, starting as early as back in the 1960s. Yes, we have variable speed limit in Seattle, but that's not the first one. The first one was actually right around Detroit. Same thing for rent metering, right? California is not the first one to have rent metering. This was a new concept, to Chicago back when they started this whole thing in the 1960s. And we've been doing this, fine tuning, and we've been perfecting our ways of understanding traffic, collecting data, building models, and proposing control strategies, really for the past 100 years almost. And car technologies were the fundamental player in traffic flow. Hasn't really changed as much as you may think. Yes, cars were not as powerful back in those days, but think about, how cars were built back in the early days. If you're fortunate enough, like me, to have driven a car from the 1990s, cars were a lot lighter. So we're basically compensating for an increase in powertrain technologies, increase in power in the internal combustion engine by adding more weight. So in terms of acceleration characteristics, we're not seeing a whole lot of major differences until we get to a very new era when we have electric powertrains, a completely different characteristic compared to traditionally the internal combustion engine that we had in pretty much the past 100 years. So here is I don't want to bore you with mechanical engineering concepts and knowledge, but here's an overview of the big differences. Before I go into the figures and the equations and what, how is power delivered, how is that related to torque, think of internal combustion engine power delivery versus electric vehicle power delivery as the difference between parking your car under the tree on a hot summer day, especially here in Florida, versus parking your car under the sun, completely exposed without trees or shades. So if you turn on your air conditioning when you get back into the car, if you parked under the tree, especially here in South Florida, the cooling effect is going to come on pretty soon, pretty immediately, versus if you had your car completely exposed in the sun, parking outside without any shades. In my experience, it takes about half an hour for you to feel the cooling effect. It is misery for the first half an hour. So that's the difference between how power is being delivered. With an internal combustion engine, power delivery is very gradual and very sluggish at the beginning because there's less air coming into the engine when the engine speed is pretty low. So you produce not as much torque, and torque, the product of torque and engine speed is power. Power remains very weak until you have high enough engine speed up to the maximum engine speed where you actually get peak power. But because your wheels can't, or the engine has to spin faster, if you want the wheels to spin faster in the same gear, right, to achieve a higher speed, but engine speeds are typically limited to, let's say, around 6,000 to 7,000 revolutions per minute, or RPM indicated here. For longevity of the engine, also to prevent overheating, we have transmissions, and we would use a different gear to bring the engine speed lower to allow cars to go at a faster speed, and while maintaining a relatively lower engine speed. And then once you start changing gears, you're back down to an unfavorable zone where you don't have a lot of power in the internal combustion engine. And the internal combustion engine is also very finicky in terms of efficiency. It has to stay kind of in this green box that I just laid out right here when the engine speed is very low and the power is very, very weak to achieve high fuel efficiency. So there's really just a lot of conflicting interests here. And for the most part, we tend to drive our cars around, no more than 3,500 revolutions per minute for any normal driver. For the longevity of the engine, and also prevent any discomfort from vibrations and things like that, and overall for fuel efficiency. So in reality, the peak power you get when reading the specifications before you buy a car, it has nothing to do with your everyday driving. So you're actually really not going to get to that. Even if you are somebody who pushes the vehicle to the limit, like right here, you have to deal with the transmission and changing gears and not being able to maintain that peak power all the time. Versus with an electric car, you have that instant peak torque that gives you very high power very quickly in a zone, in a region, in terms of engine speed that is much more reasonable, much lower, much more attainable in the real world. And since electric powertrain is quite efficient at all different engine speeds, it really doesn't require a transmission. So there's no delays in the drivetrain as well. And most importantly, it's not just the acceleration, it's also braking. Braking kind of feels just like acceleration. It's also got that immediacy that you don't have with internal combustion engine. Internal combustion engine relies on friction brakes rather than regenerative braking to charge the battery. So it's kind of working backwards in the electric motor to charge the battery, and the response is almost immediate. To put that in perspective, you can get significantly higher deceleration or significantly more severe deceleration just by lifting off the accelerator. This is actually a term called one pedal driving in the electric car world. In fact, based on my measurements, you can easily get 0.2 G, so close to 2.0 meters per second square of deceleration just by not pressing on the brakes. So you can technically drive with only one pedal and manage your everyday driving situations. And in my observations is that 0.5 G of deceleration or acceleration, it's quite attainable. You don't really have to plan ahead and push the vehicle very hard. It's quite attainable in the real world. Something I heard of 20, 30 years ago when we only had internal combustion engines without any kind of electrification. But the big concern is how we're going to charge those cars, right? And that's been preventing wider adoption of electric cars. So we started our conversations in the electric car world with those earlier models like Nissan Leaf, the Kia Soul, the Volkswagen e-Golf, if you remember those cars, that had less than 100 miles of range and that took hours to charge. The very first EV back when I was a graduate student, you couldn't really charge that very quickly. It requires an overnight charge. And if you're lucky, you might be able to go 50 miles. Today is very different. In fact, for most of the electric cars you can buy, the mainstream ones, it doesn't have to be a luxury car. You're expecting, close to 300 miles of range, and some of the good ones will deliver closer to 400 miles of range. So back in the day, we used to only have the wall chargers, the plug that you use to charge your laptop or a cell phone. Those were very, very slow. Those were only delivering somewhere around 1 kilowatt of energy. And that for today's electric car could take you, several days, approximately 60 hours to charge it full. But these popularity of level 2 chargers really enabled faster charging. So if you want to get the expected range, all it takes is, an all-day charge or overnight charge when you're at home, all-day charge when you're at work. In fact, where I am in my university, I have a level 2 charging, so it's just a matter of parking the vehicle at a charger during the day you're in the office, and you can actually get a pretty good amount of range. Really, this is typical mileage of an average American driver for a week, around 300 miles. A lot of Americans actually drive a lot less than 300 miles a week. So the bigger question is, what about long trips, right? You see in these pictures, this is a level 2 charger. You have your DC fast chargers for longer trips. These are public charging facilities that are meant to get you going very quickly with a very quick charge. Typically, we can see much higher output, 100 kilowatt at least. Tesla has its, supercharger network, very, very reliable and extensive supercharger network spread across the country. You technically could drive across the country in the Tesla, and there are even chargers for you to fill up in places like Wyoming, rural Wyoming, I-80. Typically, on average, we're looking at about half an hour to charge from 10 to 80%. But some of the most advanced and some of the best EV models, such as the Hyundai and Kia products, could do it in about 18 minutes or even less. So we've come really a long way, and the market share of electric vehicles has definitely increased significantly, especially over the last couple of years. Nationwide, it's about 6% for new cars, and we're looking at close to 20% in the state of California. And the other big elephant in the room is that we really start to have automation and driver assistance paired with newer technologies. For those of you who are in this webinar series, I don't need to give you too much descriptions or too many introduction. You know that we currently have vehicles that are level 2 capable using ADAS with ACC or adaptive cruise control and lane keeping. And it's just a matter of a few buttons, turning it on, setting a desired speed, and setting the distance you want to follow. It can automate basically longitudinal car following by decelerating and accelerating for you while maintaining a safe speed and following distance and even come to a complete stop when needed, as shown by this animation. So given all of those, right, so how attainable are they, right? It's quite attainable. It's more common than you think. So automation is, well, some degree of automation, not full self-driving, not level 3, 4, or 5, but driver assistance via level 2 is pretty much available across the board. These are the top 25 best-selling vehicles in the US. Yellow means the vehicles have ACC as optional equipment. Red means that they're standard. You can see that electric vehicles are starting to come into the list of best-selling vehicles in the United States. So you can see 2 of the Teslas here. Actually, Tesla Model 3 sold about almost 200,000 units last year in the year 2022. Same thing with Model Y. So we're starting to see more mainstream or more popularity in driver assistance technologies at the same time with electrification. I'll tell you that there's a lot of positives about electrification, especially when you look at the future with more driver assistance and automation. But the takeaway is that not so much when you have not the best hardware, which is internal combustion engine. I'm sure some of you have talked about or have met me and talked about this with me back at TRV, but I'm going to give you some of the details, some of my recent efforts, field experiments. So going forward, given all of these changes, right, we have electrification and driver assistance automation. What does that really mean for us moving forward as transportation researchers and traffic engineers? Well, we need empirical data, right? Without conducting experiments, without observing how these new technologies behave, there's really no way for us to build models. Modeling is ongoing work. Empirical data collection has been completed, and hopefully we'll be able to answer questions going forward with traffic management and traffic control. And this is kind of a 3-step process that's been really undertaken by earlier researchers for the last 100 years, right? As you saw, the data collection efforts back in the 1930s, as well as the development of the fundamental diagram, followed by more innovations in traffic control strategies, variable speed limit, ramp metering, just a few examples. And you could even say managed lanes as well. So in terms of data collection, we have to rethink the way of doing things. We have to reinvent the wheel in terms of how we gather data, how we understand traffic, because you just simply do not have the luxury to collect data macroscopically. Macroscopically using, let's say, helicopters to take aerial photographs, or, for example, mounting a camera on top of a highway and collect video data. Why is that? Because the technology is not mature enough to have high enough market penetration. And on a different note, cars do last longer these days, and it takes a while for the fleet to update itself. So if we take this rather reactive approach that's been done in the past by transportation researchers and traffic engineers, we gotta wait a few more decades for us to see a traffic stream with high enough market penetration of ACC and ACC with electric vehicles. So the more proactive, a different way of thinking is designing controlled experiments and collecting trajectory data to fully understand or try to capture all possible traffic conditions as much as we can using modern technologies such as GPS and OBD data or onboard diagnostics data from the onboard computers to construct things like time-space diagram, right? To understand vehicle trajectory behavior in a microscopic level, rather than looking at car following rather than macroscopic metrics such as flow and density of several lanes in this example. That is simply not feasible at the point. That will actually delay the effort if we go with this approach. It can mean that there's more decades to come before we understand anything. So fortunately, there's been a lot of effort on data collection for ACC, and here's a summary of the different kinds of data being collected. The summary tells you that there's a lot of concentration of data with higher speed ranges and small speed disturbances, and with a focus mainly on the concept of string stability and from a perspective of vehicle dynamics control. There has yet to be, until I perform my experiments recently, there has yet to be quite an extensive data set on traffic, on trajectory data to model car following and to integrate into microscopic traffic simulation. So my intent is to fill in the gaps. So I bought 3 vehicles and I got rid of them in the fall of 2022. They actually appreciated in value over time. Thanks to inflation, thanks to the crazy car market that we're in. So I installed GPS units. I deployed data loggers of OBD, and here's a picture of how we get data from the OBD. There's a port, just like how you diagnose engine problems. We installed, different kinds of GPS units. In the older days, we had lower resolution GPS that were much more expensive and cumbersome, but GPS technology has improved a lot. Now that you can just spend a couple of $100, all you need is Bluetooth on your phone, and you can collect data at 25 hertz. So over the course of about 2.5 years, I logged a little bit over 20,000 miles on these internal combustion vehicles with ACC. So you'll see the fun stuff with electric vehicles in just a bit, but let me show you why electric vehicles are important by telling you about the flaws of internal combustion vehicles, especially when paired with driver assistance technology such as ACC. So this data set will be available once our papers are accepted and published. So this data set is called MicroSim ACC. It's meant for microscopic simulation. So we have a lot of trajectory data covering various ranges of speed fluctuations like this. This is just an example of free flow speed of 60 miles per hour and the different extents of speed fluctuations. So lots of repetitions as well. So the big data set hopefully will be available soon for the rest of the research community. Be on the lookout. I'll make announcements as we progress. So this is to simulate when we have free flow conditions followed by approaching the back of the queue in crazy bottlenecks like this, where you have a lot of weaving or a very complicated off-ramp, or just simply many lanes merged together. And at the end of the day, we have queue discharge in a controlled experiment that we're trying to simulate by returning to free flow speed. So we selected very empty public roads in mostly the Florida Everglades area. We conduct the field tests during off-peak periods on level terrain, where the road geometry is also perfectly linear. Quite easy to find here in the state of Florida. And just to give you a few examples of the videos, you can see from a glance that the ACC system doesn't really adopt very long or very short headways. You would expect some degree of driver assistance and automation would reduce headways and improve capacity, but not so much. But here's what happens when you have some kind of speed fluctuation from a disturbance that we simulated in the real world. So you can see, problem is that during queue discharge that we try to simulate, the acceleration from the internal combustion vehicle is quite sluggish at the beginning. And you could attribute that to reaction time of the controller, but maybe not so much. But it's really, when we look at the speed versus engine speed actually versus time plot, it appears that it's it's mostly a powertrain issue. There was very low engine speed, very low acceleration, very low torque at the beginning, before reaching a relatively steady and constant acceleration. And see what happens at the end of the video. The headway and spacing actually increase at the same exact speed compared to before. Of course, if you set your desired speed high enough to make the following vehicle here exceed the leading vehicle speed as much as possible before reducing the speed again, of course, you will be able to catch up, but that catch up process will take quite a lot of time. So this is reminiscent of some of the human driver behavior as well, but ACC kind of amplifies that, as ACC tends to be a lot of times more conservative than human drivers. Looking at the time-space diagram here, you'll realize that you can see pretty obvious changes in headway and spacing. So we plotted the cumulative distance traveled here. You can see the vertical difference is also becoming larger, followed by your speed versus time plot, as well as accelerations versus time plot. So you can tell that at the beginning of the Q discharge process, the blue line doesn't really achieve a constant slope right away. There's that gradual increase, right? And that's paired up with the results from the acceleration plot. Acceleration is very sluggish before the engine builds up more power to achieve constant acceleration. So knowing the difference in powertrain technologies, we would expect electric vehicles to behave much more differently and keep a relatively constant headway. So we actually went out and tested various different electric vehicles we can find on the market, especially the rental car market. The Kia Niro was one of the first ones we tested back in 2022, the summer of 2022. There's a little bit of a story behind that. One of my colleagues, Rafael Cern, who was also in the audience when he was visiting me back in late 2021, he ran into some rental car crises at the airport as he landed, and he had to choose between that and a couple of luxuries like Maserati and Lincolns, and he decided to turn down the luxuries and went with the forward-thinking approach to get an electric car. And that's what really got me thinking about everything related to electric cars and their powertrain advantages after I decided to do a little field experiment with him while he had the rental car. So funny enough, when I went to California to do these field tests, and rent the Kia, or to rent an electric car, I was given the same exact car with the same color as the one that he just rented. So moving forward, I tested a slightly newer version of the Hyundai Kia Group product, the Ioniq 5. That's the most up-to-date EV architecture, followed by a European luxury brand, Polestar. It's basically a Volvo with a different badge, but that's also electric. We stay consistent with the experiments using the internal combustion engine vehicles with the Toyota Corollas in front as much as possible. In some cases, we use slightly different vehicles, but we made sure that the Nissan Versa, the Toyota Camry you saw, had relatively similar power to weight ratios. For the electric cars, we also made sure that they had relatively similar power to weight ratios compared to the Toyota Corollas that we tested in the earlier experiments. And we wanted to show that it's really about the power delivery. These vehicles have a little bit over 200 horsepower. Yeah, sounds like a lot more than the Toyota Corolla or even the Camry, but keep in mind that the electric vehicles weigh a lot more. They're, for example, that Polestar is about 4,600 pounds. The Ioniq 5 is 4,400 to 4,500 pounds. So these are the mainstream. I'll get to the other picture in just a bit. I know there's another picture I haven't covered, but these are the mainstream EVs we could find in the rental market with a reasonable range for us to do testing, but not too much power to make the comparison not fair compared to our earlier experiments. And who could forget about Tesla when we talk about electric cars, right? So we rented the Tesla as a follow-up to collect some additional data to do a comparison as well. And you'll see that at the end, in just a few slides, you'll see some surprises about Tesla. Nothing positive. That's my warning for the Tesla results. So because of rental car availability here in the state of Florida, at the time of the experiments, EV rentals were not very readily available. So we took a trip to Dixon, California, to set up similar experiments that compared to the ones we did in the state of Florida. Again, using very remote areas during off-peak hours on perfectly flat roads with linear road geometry. So it's just right outside of Davis if you haven't been to that area. Here's the surprise, right? With electric cars, maybe not so much of a surprise after knowing the powertrain characteristics. It pretty much maintains a relatively constant headway, and you can tell that the headway is actually quite a bit shorter. We measured about 1.2 seconds. Thanks to the regenerative braking, you can actually adopt a short headway and still brake in time, because the regenerative braking, that one pedal effect, really gives you immediate braking if something is about to happen. So a shorter headway, meaning tailgating, is not as unsafe as you think. So you can tell that the headway doesn't really increase from the video. It maintains a pretty constant headway, and this is very beneficial for just real world traffic when you have a lot of merges and lane changes. I'm sure you guys are aware of the concept of capacity drop. That's actually one of the causes of capacity drop, just having lane changes and disruptive merges, causing vehicles to fluctuate in speed, and this fluctuation would actually lead to an increase in headway during Q discharge, but you didn't really see that here in the electric vehicle. So the Hyundai Ioniq 5 as well as the Polestar gave us very similar results. Same thing for the Kia Niro that we tested. There's quite a lot of potential for high capacity, and as you can tell by the time-space diagram, right, the space, both in terms of the time in the horizontal direction, also distance in the vertical directions, they remain practically constant before and after the fluctuation in speed. Most importantly, you can see the mechanism, right? The speed of the following vehicle. So the red line shows that really the acceleration it's practically immediate. There isn't much of that slow curve before a constant slope. Here it's quite responsive in comparison. But you gotta not forget Tesla, right? When you talk about electric vehicles, you really have to think about Tesla. But unfortunately, for those Tesla fans out there, the software tuning doesn't really take advantage of the EV powertrain characteristics. So we decided to single out Tesla as a non-traditional manufacturer, and we did some experiments with that. And this will look very deja vu to you because it just looks like the internal combustion engine's car following behavior under ACC mode. Very similar to the Toyota Corollas and Toyota Camrys that we tested. So here's the congested speed we simulated, and watch what happens during Q discharge. So they don't call it ACC, they actually call it autopilot. And this is very similar to an internal combustion engine. Does it have the potential to perform like the Hyundais and Kias we tested, like the Polestar? Yes. I mean, this is theoretically a much better car in terms of power to weight ratio. It's actually much lighter, 3,600 pounds instead of 4,500 pounds, while delivering the same power. But for reasons that I either don't know or I don't want to get into, this non-traditional, also the most popular electric car brand at the time, right, does not perform the way that we actually expect. So what we did is we also selected higher set point speeds or desired speeds compared to the lead vehicle to see does it perform that catch-up process. Yes, it does, as you can see. But that process, if you look at the time axis, it takes about almost 30 seconds. So in the course of 30 seconds in real-world traffic, new fluctuations of speed could happen from lane changes, from merging maneuvers, for example, from off-ramp diverging maneuvers, and that catch-up process wouldn't really complete in the real world, so you would have more disruptions in it, and it'll just the headway will keep increasing over time, and the increases in headway will accumulate. So that's certainly not very good for capacity. So it's not just about the hardware, which is electric powertrain's advantage with that instant peak torque and very strong regenerative braking to allow for shorter headways. But we have to think about software tuning, right? So one manufacturer could tune it very well versus another manufacturer could not tune it very well. What I see from also anecdotal evidence, having rented more ACC equipped vehicles with electric powertrain, is that typically the traditional brands, basically all the brands besides Tesla, or any other startups like Lucid or Rivian, would actually perform pretty similarly. Part of the reason could be just because they source these equipments and modules from the same supplier, and we're really in a global network when it comes to auto manufacturing. Versus Tesla kind of does its own thing and even has its own insurance company. So at the same time, I'm not very surprised to see such large differences. Of course, on the data collection side, we were able to do some field experiments on lane change car following. So this is what you saw, was not an accident. Okay, on top, it was actually just ACC doing its job, what it's supposed to do. So with that kind of short headway, just a little bit over 1 second, there was no emergency brake warning or anything like that. The electric powertrain, both in terms of brake and acceleration, handled it quite well. Versus in this video you saw with the internal combustion engine, first of all, it cannot adopt a very short headway. This is the shortest it can go. And after that disruptive lane change, the headway also increases. Versus in the electric car, especially if I play it here, pretty short to begin with. Even with this very disruptive maneuver, it does pretty well to accelerate quickly and recover that headway very quickly as well. So what do we do out of the data, right? So what about modeling? So the next step, knowing knowing that we have all the empirical data, modeling has to take place a little bit differently. You cannot have a macroscopic model as easily, given the fact that there's lack of macroscopic data, but rather we want to model at trajectory level, at the microscopic level, so that we can adopt the microscopic level in simulation. My goal here is to integrate that into commercially available simulation software. With simulation, we can actually see the long-term impacts with different kinds of hypothetical scenarios when the market penetration increases. So despite the fact that we have a low market penetration right now, carefully planning trajectory data collection and developing models to integrate into simulation can really help us in the long run. The model framework is kind of based on, for ACC, is kind of based on the constant headway principle of ACC control design. And to do that, what we have here is the gap regulation. This is part of an earlier effort with PATH, and also part of an earlier effort in data collection that was rather limited to higher speed ranges with limited acceleration and deceleration ranges. And that's where those parameters were generated from. So in gap regulation, we reconcile the difference between the current gap between, or distance between the front and rear bumper and the desired distance. Again, so how do we get that desired distance? It's the headway times speed, and we subtract the vehicle length. And then also we reconcile the difference between the leading vehicle and the subject vehicle speeds. Of course, we apply speed regulation if the surrounding vehicles are very far away. So we just adjust for the current subject vehicle speed and desired speed of the current vehicle. For the most part, in congested traffic, the gap regulation will be what matters. But the problem is that, part of the reason why I went ahead and undertook all that very cumbersome data collection and collecting a lot more data is because using the earlier data with very limited speed ranges and very limited acceleration, what happens is that this constant headway logic, it doesn't really work in car following model of behavior, modeling car following behavior. For at least for the internal combustion engine, I'll get to the EVs in just a bit. But you see this very obvious, right? The vehicles do not adopt a very short following distance when they're at low speeds or completely stopped. So this graph compares the what could be generated from the constant headway model versus what's actually observed. So the actual observed distance between the two vehicles is actually quite small. Quite a bit larger, versus the simulated distance between the front and rear bumper is quite a bit smaller. Of course, it does not capture this increasing spacing or increasing headway effect. So the constant headway model doesn't really hold for the internal combustion engine. But for the EVs, it may be true. It is currently ongoing work that I won't talk about too much in detail, but stay tuned for later conferences. So what I did here is to apply a piecewise model where I have the constant headway model the way it is when there is a deceleration and small range of speed fluctuation, typically less than 20 miles per hour, right here in the middle, showing the green. While for larger speed fluctuations in the blue, I have a slightly different term. As you can tell with the speed used to multiply by the headway is actually a constant, very high value of free flow speed, could be 60, 55 miles per hour, depending on the scenario, to create that large difference between desired and current gap to generate a more negative value, a larger deceleration to increase the spacing between the vehicles when they're stopped or at low speeds when approaching the back of the queue. And to increase the headway, to capture that increasing headway, showing the red is the speed regulation only mode for that particular part of the model. When there is acceleration happening, there's only speed regulation rather than gap regulation. Otherwise, what happens is that the acceleration produced by the gap regulation approach with this constant headway assumption will be very high, unreasonably high. It doesn't really match the observations in the real world. But for the EV, I think there's a lot more flexibility. We can apply a model that's not piecewise, that's just a single equation, assuming constant headway, like right here, because EVs really maintain constant headways. Well, I'm going to skip over some of those optimization and calibration processes. When it's all said and done, again, this is not the EVs yet, but for the internal combustion engine, of course, we're going to expect a decrease in capacity, increase in the layoff, and lower average speeds for all of these analyses using a real world corridor. We actually did one. So just a comparison of the two extremes, right? 100% ACC versus 100% human driver on the State Route 99 corridor in Sacramento, California, where we had quite a lot of good benchmark data to calibrate a benchmark scenario for human driver behavior. So you can see all the blues are the properly functioning detectors, pretty densely put together. The red ones are partially functioning detectors, but still you see a pretty high coverage of detectors for us to build a benchmark scenario. So we actually integrated into AIMSA via the micro SDK or micro software development kit that allows to override the models within the proprietary algorithm of the simulation software. So going forward, we would expect that we could apply a simple and constant headway model for EVs with ACC, and hopefully that'll help us answer questions about, traffic safety, operations, even geometric design, right? Does that left lane, the express lane approach still really work for electric vehicles, right? Do we need rent metering in the future, given the powertrain advantages, given what you saw with the car following behavior, right? Do we need to think about improving those short ramps and short merges? Maybe not so much, right? With electric vehicles being able to accelerate so well, maybe it's not worth the infrastructure spending on such geometric constraints. And obviously, with more electrification and more automation, there's definitely more excitements coming with auto lane change and possibly level 3, level 4 automation, which we'll still have to take our time and carefully conduct experiments and understand the impact on traffic flow to hopefully help traffic engineers and transportation researchers adapt to vehicle technologies and the potential opportunities as well as obstacles. So at the end, I want to thank my rather extensive list of group members who have participated, especially in the field experiments. Has definitely been challenging, but very rewarding at the same time. So that's the end, and hopefully that gave you some surprises, a slightly different perspective, and I'd be happy to chat with you guys if you have any more questions.
Thank you, David, for the great presentation. I remember your commute is such a long way, which triggered you to actively work on traffic congestion. By such experiments that you do, we now clearly see that how commercial ACCs deteriorate the traffic capacity and other performances, and also how the electric automated vehicles can help resolve them. Like by its nature, such as I remember that strong acceleration and quick peak torque. It was also interesting that Tesla does not take some advantages as other EV powertrains do. Okay, now the floor is open to the audience. So if you have any questions for our wonderful speaker, please unmute yourself or to cast a question, or just leave it on the chat box, please.
Before you guys ask, just FYI, right after I did the experiment using the Teslas, it also correlated with the time when the Tesla stocks were dropping. So, funny enough, right?
That's funny.
That's the inconvenient truth.
I love your sense of humor.
Any questions from the audience?
Hi, I have a question. Can you hear me?
Yeah.
Yeah, my name is Wano from South Korea. It's a perfect time for me. Usually the seminar is like 11 a.m. Eastern time, which is like a midnight or 1 a.m. in the morning. But now it's I can still enjoy the presentation without sacrificing my nighttime sleep. And my question is, I think there are some different driving styles you can select on autopilot in Tesla. Do you think it makes any difference? For example, they have a Mad Max, right?
Right. So during the experiment, we want to see what's the true potential, right? So what we cared about is, given this better hardware, which is electric powertrain, with better braking and better acceleration and power delivery, what's the potential for car following? What's the potential for possibly capacity? So we selected the most aggressive setting, and that's what we got. Yeah, there is a more economical setting that we did not select, but I would expect it to be probably even worse. We select the maximum regenerative braking, right, to capture that immediate braking effect. But again, unfortunately, we did not see that. We rented the most recent ones. This was done back in December 2022, so we rented the latest 2022 model. Who knows? Maybe this needs another over-the-air update later. But it's surprising. It is surprising that all the other manufacturers were doing something very different compared to Tesla.
And I have one more question. Again, thank you for a wonderful presentation. I think I can. I think the capacity, if you have 100% electric vehicle, and then if you have 100% internal combustion engine vehicles, do you think that there's a differences in terms of capacity?
I would definitely expect so. So again, some of the ongoing work I have not presented yet, but I'll be able to share. Let's say the next TRB, for example. The analysis I did, the modeling is, for now, the work is only completely done for the internal combustion engine. I would expect a significantly different model for the EVs. Notice how I pointed out that there's a shorter headway to even begin with, while the EVs actually maintain a very consistent headway. So there's not much of an increase in headway when there is unstable traffic. So when it's all said and done, yeah, I would expect definitely significantly higher. What we observed with an internal combustion engine with ACC is, 1.6, 1.5. That's the best it could do for headway. And that headway cannot be sustained, which means that, the maximum flow or capacity cannot be sustained in the real world if you have enough of those. So I would expect quite a significant improvement. I'd say at least 50% higher in more ideal cases.
Thank you. I have one more additional question. For the capacity model, so do you think it's possible that the future capacity model is like a function of percentage of capacity the electric vehicles in the traffic flow stream, and then percentage of internal combustion engines?
Yeah, the whole purpose or the long-term goal of this research, right, using microscopic level data to build microscopic level model and develop simulation tools, is for these microscopic level simulation tools to give us macroscopic estimates, and which in turn could be, let's say, part of the highway capacity manual recommendation in the future. Yeah, so until my group finishes the microscopic simulation development of EVs, we won't have a concrete answer for that, but that's coming up. It's actually within about a year, we should be able to have a good outline of how does it change, how does the capacity change when there is different market penetrations of electric vehicles with ACC. So look forward to sharing that, hopefully next TRB.
Thank you.
I hope there isn't any Tesla owners here in the audience.
I hope not. I want to ask a question at this moment.
Go ahead.
I found your experiment really interesting, as most of the experiments and data until now does not include electric ACCs. I like that, especially you mentioned, thank you for the inflation. I'm just kidding. I think you used different car models for the experiment, such as Ioniq 5 and Polestar.
Right.
Are those vehicles used in the same order when you run the experiments, if those were in the platoons?
Yes, they were always serving as the falling vehicle. We always had very similar lead vehicle behavior. So we controlled for these discrepancies.
Oh, I see.
And we follow the same procedures by using, different selections of gaps adopted by, or headways adopted by the ACC control. So there's usually medium, long, and short. So we tested all of them for the same number of repetitions under identical conditions. And in addition to that, we even vary the temperatures. So when we conducted the experiments in the summer, we were able to experience and collect some data when there were days where it was 98 degrees outside in right around Davis, in inland California, but there were also days that were 28 degrees Fahrenheit in the morning, so below freezing, right around Davis, California, to kind of give us a bit more variety. And we saw pretty consistent results under various temperatures and different conditions. I know that the electric vehicles, electric powertrain, especially with the batteries, are very sensitive to temperature fluctuations.
So you mean that experiment is like lead vehicle followed by Ioniq 5 or lead vehicle?
Exactly. The Polestar, the Kia Niro, and the Tesla.
So there was not the cases like lead vehicle followed by Ioniq 5 followed by Polestar like that.
Yeah. So great point, right? What if we what if we have a lead vehicle that has much better capability when it comes to acceleration? That's an interesting question. So certainly this work is is just getting started, and that's why recently NSF funded one of my projects, proposed projects involving EVs. It's very recent news, so there's definitely room for more experimentation, more data, and more work coming up. Hopefully, I'll be able to share those at the next couple of TRVs.
I hope so. I have one more question. I believe the internal ACC functions and like their performance might differ by the models. Like, did you find any discrepancies between Ioniq 5 and Polestar so far?
Not really. We conducted identical experiments, and the plots. At the end of the day, the results look very similar in terms of headway and how the headway is maintained, or whether it's maintained or not. There are some small discrepancies in just the acceleration braking, but in terms of the outcome for, let's say, potentially macroscopic traffic, it's very similar. I mean, I have in front of you the Ioniq 5 versus the Polestar car following behavior. And just an example, you can see that that constant headway is still held, and on the time space diagram, the headways and spacings don't look any different throughout the whole process with this car following experiment.
I see. Thank you for your answers. They really helped.
Well, hopefully that gave you guys a different perspective. It's with modern technologies such as driver assistance, like ACC, it's not only about software. Software can only do so much. With a better hardware, software can perform more efficiently. So hopefully that was electrifying to you guys, and you're welcome to buy a Tesla. My goal is not to dissuade you from buying a Tesla, but hopefully that entertained you with some surprises.
I really agree with you.
But in my opinion, if I were to buy an electric car, I'm a little bit biased towards the Hyundai Kia models after all my experimentation.
I see. I would definitely refer to your words if I have to buy electric vehicles.
Well, hopefully the next TRV I'll have more extensive results before more of the general public start adopting electric cars. And really the goal is we can see this additional really surprising benefit on the capacity side. We've been talking a lot about electric cars in terms of how do we charge them, or what are the emissions impact, but this is actually incredibly overlooked, but incredibly important.
Yeah, I look forward to next TRB to hear some new works from you. So, are there any more questions from audience? I think we don't have more right now. Do you agree with this, David?
Yep.
All
Um,
right. Go ahead.
Yeah, I'm gonna leave my contact info over here. You're welcome to reach out if you have any more questions. You want to discuss anything with me. Look forward to seeing everyone at TRB 2024.
Perfect. Thank you again, David, for sharing your new perspective and insights today. I look forward to your data to be open to the public in future, like you mentioned. I believe the community will really appreciate that work, and everyone will be stay tuned for your future works. Also, thank you to all of our participants for the discussions, especially who attended from Korea. Thank you for using your precious night times for our webinars. We will try to zigzag the webinar times for all needs if it's possible. We hope you will join us again for the next webinars, and you all have a great weekend and have a great rest of the day. Thank you.
Thank you, everyone.
Thank you, David.